Right, well, thanks for coming to the presentation. I'm going to quickly go through the Meteor beacon phase one, which was to establish this beacon, which is at the premises of the Mansfield and Sutton Astronomical Society, as the name suggests, near Mansfield, which is a nice central location, and it's been operating since last year. So it's got quite a lot of hours on the clock. You can go and see its status online. It reports itself online to tell you the power it's running and its general status. So you know it will be there if it says it's there. Its function, sorry, going the wrong way here. Its function in life is to illuminate a region above the beacon. The altitude at which meteors burn up is between 100 kilometers and 80 kilometers, and that's where they produce the ionized trails, which are reflective to radio, and they're particularly reflective to radio at 50 megahertz. So it's a much better scheme than looking at 2 meters, for example. And I know a lot of people observe meteors using graves, and the advantage of our system is this is showing you echoes from meteors that are actually above the UK, and that was the principal reason for establishing the beacon. So echoes from meteors can be heard out to a range of about 1,000 kilometers or 1,200 kilometers by anybody who wants to listen for them. Phase 2 of the project, which I'll describe in more detail, is to set up a network of receivers spaced well away from the beacon. Those receivers that are within about 200 kilometers are going to see a lot of aircraft reflections. But once you get more than about 300 kilometers away from the beacon, the aircraft reflections more or less disappear, and we're seeing purely meteor echoes. And they're coming in at quite an amazing rate. If you look in the morning, the best time to look is in the morning when the planet Earth is facing into its direction of travel round the sun. You'll see more than you will at other times. There are random ones at other times, but that's the best time to look. So take a look on 50.408 megahertz in the morning, and you shouldn't have to wait long before you hear a few meteor pings. First of all, some very basic bits about meteors and their echoes. I don't know whether I can get the pointer up there, probably not, but we've considered them as being in 2 parts. There's a head echo, which features very rapidly changing Doppler shift. That's this bit here, as the path length from the transmitter to the meteor to the receiver is changing very, very rapidly. Oh, thank you very much. That's the head echo, that little stripe there. This is a standard waterfall display, just in case anybody's not familiar with it. You've got frequency across here, time is running down here, brightness is indicating the signal strength. So the head echo, it features very rapidly changing Doppler shift as the path length of the reflection path changes and the meteor decelerates. It then sometimes produces a tail echo, and that is more or less static in the atmosphere, and in fact, if it has any Doppler shift on it at all, it's probably related to the wind speed at the altitude at which it's occurred. The wavelength of 6 meters is particularly useful for looking at meteors. Okay, so this describes the situation with the Doppler shift. If you take a meteor trajectory like that, at T1, both the path from the transmitter and the path to the receiver are reducing, so you'll get a positive Doppler shift. At some point, if you get a midpoint like that, the Doppler shift will drop to 0, and if it's still producing reflective ionization, you will see the Doppler shift go negative. And it's very important. The Doppler shift is something that's going to be very important to us in making serious measurements about meteors. So the head echo lasts just of the order of 10 to a few hundred milliseconds at the most. The tail echo, which we will go on to now, this bit, can last for seconds or even minutes. And that's the thing that we use for radio communications purposes, for for meteor scatter contacts. The head echo is not much use because it's such rapidly changing Doppler shift and the time span is so short. You can see from the amount of, remember the time scale is vertical and there's only milliseconds in this particular example here. Here's an example with a much more impressive bit of Doppler shift. The constant line through there will be an aircraft echo. This is an echo received by me. I'm about 200 kilometers from the beacon. I'm too close to it from an aircraft point of view. I can't get rid of them. But here is one that started off with a Doppler shift well off to the screen here, so certainly more than 500 hertz, which indicates that the path length of the reflection path length was changing at about 2,500 kilometers per hour or more. In this case, the tail echo lasted for ages, as you see, and was a nice strong tail echo, and you could have a complete phone QSO on that, on the strength of that, if that's your aim. Using a waterfall display to show the echoes is very interesting. It shows all sorts of strange things going on. And these are examples of what I think the astronomers like to call epsilon echoes. There are various possible explanations for them. They could be where the meteor has broken up. There are other explanations I've heard. I leave it to you to come up with your own answers, but some of them are really quite weird. But this is the sort of thing you can expect to see if you tune a software-defined radio to the frequency. You set the span at about 500 hertz. The full 500 hertz is not being shown in these images here, but you'll see lots of interesting things like that. Very often you see an echo with multiple tails. That will be where an echo or the meteor has perhaps passed through two or three regions of the ionosphere and has left a static field of ionization behind it. And you quite often see these multiple echoes. Excuse me. Okay, so I like to think of the tail of the echo as behaving much like a wire. This makes me a complete heretic in the world of astronomy. They like to use words like specular, which in my dictionary means mirror-like. I don't think they're at all mirror-like. I think they behave like bits of wire. Optical observations of meteor trails tell us that the diameter of the sparkly trail you see behind a meteor is of the order of a meter or two. It's of that order. There are radar papers I've seen that suggest that the ionized bit could be 1.5 meters in diameter. I don't actually believe that. I think it would be smaller than the optical because of the sheer temperature, but I don't know. I'll leave that to others to sort out. But basically what you've got is a cone, if you like, or like a little cylinder of highly ionized material behind the meteor as it's burning up, a sparkly tail behind it, and as it goes through different regions of the ionosphere, perhaps the ablation of the meteor reaches a peak, or perhaps it passes through an area that is more predisposed to being ionized, and it leaves a static plasma behind, which produces the tail echo. So echoes, or the tails, are cylindrical. That's an important thing to bear in mind. As I say, the visible meteors trail sort of the order of a meter in diameter, and they can be thousands of meters long. They can be maybe even low tens of kilometers long, depending on how much material is ablating off the meteor as it burns up. So there's another typical, very short-lived head echo, and there's the tail echo. Now, if it behaves like a wire, we're illuminating the field with circularly polarized radiation from the beacon. And if it's behaving like a wire, I think it will pick up radiation, or it may pick up radiation, and it will re-radiate it as linear polarization according to the trajectory of the meteor. And this is rather important. And to a lesser extent, the tail echoes seem to me to exhibit this property, although that's something I would like to explore in much more detail with a certain gentleman who's sitting in the audience. Good afternoon, Chris. But certainly the head echoes are quite highly directional. And this is going to be rather important in this project. Because there are things that we can do with the head echoes, possibly, that really could be very interesting. We might be able to triangulate the trajectory of the meteor. But to do that, we can only do that with the head echo. So the head echo will appear directional for two lots of reasons. Firstly, it's polarized, so if your antenna system is cross-polarized, you might not see it. You might be heavily attenuated. The other reason is that according to the length of this highly ionized region that's going to behave like a chunk of wire, it will behave like a chunk of wire and it will exhibit lodes and nulls. And the steepest null, of course, is in its direction of travel. So if it's traveling directly towards you as a receiver or to the beacon, if it's the beacon, it'll pick up no energy. And if it's traveling straight towards you, you will see little or no energy. And this was first observed, actually, by Bernard Lovell, shortly after World War II, when he was using pulsed radars to look at meteors. And he observed the fact that when they were off at 90 degrees, he saw nice big echoes, and he didn't see much when things were coming straight towards him. To try and explore this very casually, I set up two receivers, one with vertical polarization and one with horizontal polarization. This is not a scientific study. This is something that needs to be looked at in much more detail, and there's a great opportunity here for a bit of citizen science to get into this. But here are some examples. The vertically polarized system you saw this echo. They've been carefully synchronized, so those timing marks are synchronized as well as I could get them. The horizontally polarized one has seen an echo here that's not really visible on this one. This one corresponds as a faint one there. I don't know about the bottom one. Here's another synchronized one. This time they're reversed. The horizontal one is on this side. And you'll notice that the aircraft echoes tend to be more horizontally polarized than vertically. It rather depends on where the plane is flying and how much gin they're spilling as they're flying along, I guess. But again, you can see the horizontal one has seen these echoes here. This one's missed that one. Well, it's only very, very faint. I thought I had an example where the vertical was strong. You do see them. It's going to be completely random, the polarization, or fairly random. And I suspect largely linear, possibly elliptical. And of course, if you're viewing the echo from a long way away, you've got to think about Faraday rotation as well. So it's a big area to look at. So, moving on to the phase 2 of the project, which has always been to set up a network of receivers, and to do this in two ways. One is the RSGB Legacy Fund has kindly funded the building of 3 prototype receivers, which will stream to a server. In fact, the first one's already doing so, although it's not quite in the form we want. Individuals will be able to build receivers to that design and join them into the network. If they're going to do that, they'll need to follow the design. The design will be open source and fully published as soon as we're happy that we've got it somewhere near right. And a key part of this is because the bane of the radio astronomers everywhere is noise, and not everybody has a quiet location. So we are looking specifically for quiet places where we can locate these, the first of these receivers. And anybody, any radio amateurs whose location is quiet and who doesn't want to do a lot of transmitting on 50 megahertz would be very interested to hear from them, of course. But the first of the receivers has gone down to the Norman Lockyer Observatory down at near Sidmouth. It's installed, and it is actually streaming data. It's not in a form that I'd want to invite you to look at the moment, because the displays are not right and there's more software to do. But we are, I feel, now only weeks away from being able to have that data accessible by anybody who's interested in meteors. And of course, there's no reason why you shouldn't build your own receiver and receive the echoes from the beacon. This is the internal workings of the receiver as it presently configured. It's based on an SDR Play RSPDX. There's a Raspberry Pi in it. There's 2 GPS receivers. That may sound a bit over the top. A Leo Bodnar provides a frequency reference, because one of the things we're going to want to do is to make very accurate Doppler measurements. So it's vital that both the transmitter and the receiver are locked to accurate sources. So, and the Leo Bodnar also feeds into this. So it feeds through this unit here to the RSPDX to lock its oscillator, or to provide its local oscillator. Also in the timing module is a little U-Blocks receiver, which produces timing pulses synchronized to UTC within about 100 microseconds, maybe a bit better than that. And the 24 megs is also used to generate a signal, an in-band signal, at a very low level, which is injected into the front end of the receiver. Because in order to get the accurate timing we want, we've got to take account of the latency through the receiver, any processing in the receiver, through the Raspberry Pi, and across the web. So the timestamps, we can show you the timestamps, look like this. They're actually put in at a very low level, 2 kilohertz away from the beacon's frequency, and they are modulated in length to indicate the minute rollover, and they also encrypted to show date and time, and other data can be input there. The timing module has been designed by Andy, G4JNT, and when we've got the design satisfactory, we will probably get it made, at least partially populated, and it will be probably available through the UK Amateur Radio Association on a not-for-profit basis for anybody who wants to build their own setup. That's the plan as it goes at the moment. Now, an ambition is to do this triangulation. I should hasten to add that there are lots of other things that we can do, like comparing radio meteor echoes with optical observations and general meteor counts, the magnitude of the echoes, and all sorts of other stuff. I'll show you a link to the science objectives of the project. But one of the ambitions, once we've got this data streaming, that will be the end of phase 2, but phase 3 might be to try and use that Doppler data, correlate the Doppler data as observed from multiple directions, and calculate the trajectory. And if there's anybody here clever enough to do it, please come and see me afterwards. But we think that's a genuine viable project once we have the data. So at the moment, that's being done by optical observations, using cameras pointing up towards the sky by an outfit called UK MON. There are other organisations there. I think there are about 3 or 4 camera networks, but the most popular one is UK MON, who have about 200 cameras pointing skyward. The various networks are coordinated by the UK Fireball Alliance, and that's led by a guy called Dr. Ashley King at the Natural History Museum. And anybody who's watching the news about the Osiris mission and the bit of rock that's come back from an asteroid, he was on the telly the other day. The samples will be going to his department. We're in touch with him. He knows our project exists. We haven't told him we can do it. We told him we're looking into doing it. And they're very interested because what they're interested in doing is recovering meteor material that actually makes it down to planet Earth. Excuse me. So UKMON is the organisation who have the 200 cameras, and roughly, very loosely speaking, the way they work, they point up in the sky. If it's a clear night and they see something that looks like a fireball, they log take some pictures. Their first level of filtering is they will only take it if they can identify 4 stars. Otherwise, they could be triggered by all sorts of things. So they know they've got 4 stars in the image that are known and they're in the right place. And in the morning, the data gets sent off to Canada, where it's crunched, and they will then work on producing the trajectory to work out the origin, the radiant that the meteor appears to have come from, and if it's likely to hit the ground, then where it might have landed. And you might have remembered the case of the one that somebody found on their drive in Gloucestershire. Well, that was jolly good, but there was another bit of it, which you don't hear about quite so much, which was tracked down in a field some way away, and that was tracked down by this system, and they actually recovered the rock. And there is another project in Australia based at the Curtin University in Perth, which called the Desert Fireball Network. And this is funded actually by the Australian government, and they've got cameras dotted around, and they're trying to find lumps of rock that might land in the Western Australian desert. Now, of course, these only work at night time, and this is another opportunity for us if we can develop this technology for us to assist. Ooh, wrong one. You can find our science objectives, the project science objectives, on the UK Meteor Beacon .org website. This is a short list of them. There are other objectives that the astronomers are more keen on, things like simple meteor counts, and so on and so forth. And I think there are all sorts of related things, such as the study of the effect of meteors on the ionosphere, in which we have our own specialists here who will be very interested in meteor counts, and maybe if we can classify them as well. One of the objectives of looking at radio echoes and comparing them with optical echoes is to see if we can correlate in any way the different forms of echoes that we see with the material from which the meteors are made. Okay, before I go on to that, I have bought one of the receivers here, and I'm very happy to pass it round if anybody would like to have a look at one. It's a bit chunky, but perhaps I could start by passing it round. Oh, I would do, except I forgot to take the cover off, but it's only 2 screws, so it shouldn't take me more than a second. The receiver, as I say, is based on an RSPDX and a Raspberry Pi, so it's not an expensive setup. Here we go, if anybody would like to marvel at it. I do apologise about this low standard of metalwork and so on. It is entirely made on my workshop, which is not much better than the kitchen table. But it sits there, it receives about 10 kilohertz chunk of bandwidth around 50 megs, streams that as IQ data out to the server, and provides the precise timing signals. Sorry about the bits of VeriBoard with respect to the last lecture, which we really should do better. So I think there's huge opportunities here as a sort of citizen science type project for us to do some serious observational work with meteors, their effect on the ionosphere in particular, and work towards providing an alternative way of tracking down the meteors that actually arrive on planet Earth. The other thread for this project is that children of all ages seem to be very fascinated when they see echoes from meteors. And whenever I've done open days and been looking at the Graves radar, for example, their eyes pop out when they see all these echoes from meteors. And so it will be if those meteors are directly above them, i.e. over the UK. So it's a really good tool for developing STEM-based projects. And this is an area we'd really like to develop, and we're really looking for champions to help us develop it. You can get started at a very low cost. You can get echoes if you're lucky with one of these RTL dongles, price £12, I think that one was, and the Moxon antenna made according to the wonderful instructions available on the internet. I think the material cost is reckoned at £4, and it's a really good directional antenna in that it has a very high front-to-back ratio. And when it comes to eliminating local sources of noise, that can be very useful. It's also sufficiently directive that if you point it up into the air, which you need to do, you need to point it at the center of the illuminated volume, i.e. point 100 kilometers above Mansfield, basically, then that again helps reduce the electrical noise, which is a problem at 50 megs, as I think we all know. So not every school that puts one of these together is necessarily going to have immediate success with hearing lots of echoes, but they'll learn a bit about radio, and they'll learn a little bit about EMC and interference as well, most probably, which is no bad thing. If you want to do more serious work, then something that you can lock to a reference to make those precision Doppler measurements is essential. If you're not too worried about that, the FunCube dongle works well, but you can't lock that. And these echoes are certainly quite usable, quite easily receivable out to a range of certainly 1,100, 1,200 kilometers. I was visiting a friend in Sweden the other week, and he had a 3-element beam. We pointed at the beacon. We were immediately rewarded with loads of echoes. But this is an area where we would like to get more people involved. Have I gone the wrong way again? We'd like to get more people involved. Of course, the software that the kids would need for a STEM project is all available free. I tend to use SDR console, but other software is available, of course. I get on particularly well with that, and it can be made to show the head echoes nicely. Doing it again, aren't I? So there you are. If you'd like to participate in any way in the project, please let me know. We're particularly interested in developing the STEM potential of this project. We're all rather focused in getting these receivers built. And the software's got to be sorted out, and the display software and the streaming, which is very close. We're very nearly there. And then I've got to get 2 more receivers, homes for 2 more receivers. The perfect places for them would be on the east coast of Ireland, somewhere north or south, and somewhere north of the central belt of Scotland would be perfect places, nice radio quiet locations. And what we need is the quiet location, which might be an Astronomy Society's observing site. We need preferably somebody nearby who understands radio and can go and make an assessment of the noise level and whether it's likely to be a workable site, and also perhaps help with the installation. The installation's not very complicated, but it does need a little bit of radio expertise, and it needs a little bit of networking expertise. So if anybody wants to join in, please let me know. You'll be very welcome. perhaps when we move on to some questions, if anybody's got them, I'll just run through a whole lot of Meteor echo screenshots, and you can see what amazingly different things you're likely to see. It's I don't know whether this will work on your presentation, but we will give it a try. Oh, I'm down there, aren't I? I'm guessing we're there somewhere. It's difficult to know where the pointer is, isn't it? Come down here somewhere. Oh, I've lost my pointer. I think I probably have to give up on that one. But in a minute, perhaps after questions, I'll set it up showing lots of meteor echoes. So, there you are.